This study presents a comprehensive analysis of the structural, morphological, and optical properties of ytterbium-doped indium oxide. A series of characterization techniques were employed, including X-ray diffraction, XRD, Raman spectroscopy, UV-vis spectroscopy, photoluminescence, PL, scanning electron microscopy, SEM, and X-ray photoelectron spectroscopy, XPS. Undoped In2O3 and samples doped with 1%, 3%, and 5% YB were examined. The incorporation of ytterbium led to significant alterations in the crystal structure, as evidenced by shifts and intensity changes in XRD peaks and modifications in Raman vibrational modes. Morphologically, the doped samples exhibited a fibrous character with heterogeneous particle sizes, ranging from clustered aggregates to isolated fibers. Regarding optical behavior, a minor variation in the band gap was detected alongside the emergence of transitions in the visible spectrum. Notably, the results showed evidence of energy level splitting in ytterbium transitions, which may arise from spin, orbit coupling, and/or the Stark effect. The diffraction patterns show the presence of both phases within the sample, with the cubic phase being predominant. The doped samples do not show additional peaks corresponding to any ytterbium oxide. In comparison with the undoped sample reveals variations in the intensity and position of the peaks as the dopant concentration increases. This indicates that doping affects the crystal structure of the oxide. The Raman spectrum shows several characteristic peaks of In2O3 associated with different vibrational modes. Taking the peaks of sample E4 as a reference, these peaks allow us to determine the presence of shifts or the appearance of new peaks because of doping. The doped samples exhibit noticeable shifts in the peak positions. These shifts can be attributed to the incorporation of ytterbium atoms into the crystal structure of indium oxide. These differences may be related to modifications in the symmetry or degree of ordering of the material caused by doping. Additionally, an increase in the intensity of certain peaks associated with the cubic phase can be observed, further confirming the presence of a mixed structure. Through the combined analysis of Raman spectroscopy and X-ray diffraction, the incorporation of the dopant material, which significantly influences the crystal structure of the host material, is confirmed. The absorbance spectra of the doped samples show that ytterbium doping alters the electronic structure of In2O3, as evidenced by changes in intensity and spectral shifts. The absorbance intensity decreases with increasing ytterbium concentration. This may indicate a lower light absorption efficiency as the dopant concentration increases or a modification of the electronic density of states of the material. To determine the band gap value, the talk method was used. As previously known, the band gap value of undoped oxide is 2.71 electron volts. After doping the material, an increase in the band gap value was observed, reaching 2.84 electron volts, 2.88 electron volts, and 2.85 electron volts for the 1%, 3%, and 5% YB doped samples, respectively. The slight decrease observed when increasing the dopant concentration from 3% to 5% may indicate saturation or interactions between ytterbium ions that affect their ability to introduce additional states into the band gap. The main peak observed in the photoluminescence spectra corresponds to the 2F5 halves 2F7 halves transition at 1040 nanometers, which is characteristic of YB superscript 3 ion emission. This peak is located in the infrared region of the spectrum. No significant changes are observed, indicating that the emission wavelength is not affected by the different dopant concentrations. However, the spectrum exhibits a slight variation in the width and shape of the peak, which may be attributed to interactions between the YB ions and the surrounding host material. The proposed energy level diagram shows the possible transition of the YB ion. The PL spectra in the visible range of the ytterbium-doped samples do not show any transitions, since ytterbium exhibits these transitions only in the infrared region. However, it can be observed that the PL intensity is higher for the sample doped with 1% YB, while the PL intensity decreases for the 3% and 5% doped samples. The SEM micrograph of the sample doped with 1% YB shows a fibrous morphology with some agglomerated fibers. In the enlarged region, it can be observed that the different morphologies exhibit a wide variation in size, with particle sizes smaller than 2 micrometers. In the EDS analysis, carbon is observed because the sample was placed on carbon tape. Oxygen and indium are uniformly distributed throughout the sample, whereas ytterbium appears to be highly dispersed, indicating that the doping is not homogeneous. In the sample doped with 3% Yb, particles with different sizes and a fibrous structure can be observed. There is also notable variability in the morphology of the structures present, ranging from dense regions to loosely distributed structures. The elemental mapping shows that oxygen and indium have a uniform distribution, while ytterbium is uniformly dispersed throughout the particles. In the sample doped with 5% Yb, agglomerated fibers forming spheres of different sizes can be observed, along with isolated structures. The elemental maps show that oxygen and indium are uniformly distributed. The doping process may influence both the morphology of the sample and the dopant concentration. The distribution of ytterbium is uniform throughout the particles of the sample. In the EDS measurements of the 1% Yb doped sample, indium and oxygen are present in relatively high percentages, while ytterbium accounts for 0.01 Wt%. For the 3% Yb doped sample, the quantities of ytterbium, oxygen, and indium in the sample can be determined quantitatively. Ytterbium is present at 1.45 Wt%, indium at 30.69 Wt%, and oxygen at 17.92 Wt%. For the 5% Yb doped sample, indium is present at 58.81 Wt%, oxygen at 21.19 Wt%, and ytterbium, which is the dopant material, at 2.08 Wt%.